Hello everyone, let's look at some proton NMR spectrums. And this first one is 1,3-dibromopropane. And this is the molecule, how it looks like. 1,3-dibromopropane. And it is a symmetrical molecule. We can identify two sets of signals or two sets of hydrogens. You see the two sets next to the bromine, they are identical, so they will appear in one single peak, and then the two hydrogens on A will appear as a one peak. So we will see two signals, right? One for A and one for B hydrogens. And out of these two signals, B would be more d-shielded because it's right next to a electron withdrawing group. So B protons are going to be this, and then the A protons are going to be here. Look, their ratio is 2 to 4, but you can see here as 1 to 2. Okay, and then if you look at protons A, right? So there are 4 hydrogens next to A because all 4 hydrogens are same. So A will split into N plus 1 due to the adjacent B hydrogens. So N is going to be the hydrogens on the next carbon, which is 4. 4 plus 1 will make it a quintet. So the two hydrogens, hydrogen A, will split into a quintet, 4 neighboring protons. And then the hydrogens on B, 4 hydrogens, will split to a triplet. 2 plus 1 is 3. 3 is a triplet due to 2 hydrogens on A. So these are the 4 hydrogens, and they will split into a triplet, 2 neighboring protons. Okay. And in this spectrum, how many different environments do we have? A. So this A, we don't have any identical methyl groups. So we have only 3 hydrogens here for the region A. And then, so this A, B, C, D, E, they are labeled based on increasing chemical shift. A mean that is the most less chemical shift or most upfield, closer to the 0. Okay, meaning more shielded ones. So A would be the most shielded, 3 hydrogens, and this is that 3 hydrogen, close to little bit less than 1. Okay, and these 3 hydrogens are next to a 2 hydrogen on C. So these 3 hydrogens should split into a triplet due to these 2 hydrogens. 2 plus 1 is 3, 3 is a triplet. So this one is a triplet. And then the B hydrogens. So there are 6 hydrogens on this carbon, 1 is hydrogen, and then you have 2 methyl groups. There are 6 hydrogens, and those are going to be in the same environment, and these 6 hydrogen will split by the adjacent hydrogen, which is this one right there, to a doublet. So 6 hydrogen is a doublet over here. So that's what you are seeing, 1.2. This is the expanded doublet right there, these 6 hydrogens. And then the next chemical shift would be CH2 hydrogens. You see here in 2 hydrogens, on the next carbon to the left you have 3 hydrogens, to the right you have 2 hydrogens. So 3 plus 2, 5. And these 2 hydrogen would split to a sextet because there are 3 plus 2 is 5, 5 plus 1 is 6, n plus 1 rule. So there would be a sextet. So the 2 hydrogens, you would see a sextet over here if you expand it. Okay. And then D hydrogens, CH2 hydrogens. These 2 hydrogens are close to a carbonyl group. So it would be the next increased or the chemical shift, next higher frequency. So these 2 hydrogen will split to a triplet. 2 plus 1, 3, a triplet due to these 2 hydrogens. So the D hydrogens, 2 hydrogen would be a triplet, that is this one right there. Okay. And then you have A, B, C, D, E. So this hydrogen, E hydrogen, would be the most de-shielded one because it's directly attached to a electron withdrawing oxygen. So E here will be splitted into 7 peaks because there are 3 plus 3, 6. So n plus 1 rule, so 6 plus 1, 7. So this hydrogen would split into a 7 peaks. So you can see that 7 here. 1, 2, 3, 4, 5, 6, 7 at 4.9. Okay, that's how you look at the peaks for this molecule. And this is the proton NMR of allyl bromide. Allyl bromide, you have 2 hydrogens here and B, C, D. So alkene hydrogens, remember, due to the diamagnetic anisotropy, alkene hydrogens are going to be more de-shielded compared to regular alkane hydrogens. So as a result, B, C, D would be more down towards down this way, downfield, de-shielded compared to A. A is closer to a halogen. But these 2 hydrogens is what you find here around close to 4. Okay, and that's good. There are going to be 2 hydrogens, and this would be splitted into a doublet due to the D hydrogen. So you'll see a doublet right there. And then the next one is going to be this hydrogen, B. So this would be the next higher frequency one. And then it can split due to this hydrogen because they are not in the same environment. So that would make it a doublet. So you can see a doublet. And then the C hydrogen would be again going to split due to this one hydrogen to another doublet. And then if you look at the D hydrogen, that will split due to C, a trans coupling, and also that is going to split due to B and also due to A. So you can see a multiplet right there. Okay. A quartet versus a doublet of doublet. Normally, if you have 3 hydrogen on the neighboring carbon, the hydrogens will be splitted into a quartet in the ratio 1 to 3 to 3 to 1. Sometimes we can also see some peaks, they are on the same height, and we call them as doublet of doublets, and their relative intensity is 1 to 1 to 1 to 1. The proton NMR spectrum of ethyl benzene. We can identify how many different carbons here. There is a methyl group, 3 hydrogens, and then you have 2 hydrogens here. They are outside the benzene ring, so they would be more upfield, meaning closer to 0. And then the hydrogens on the benzene ring, again due to the pi electron cloud and due to the diamagnetic anisotropy, you can see that these hydrogens, they would be more upfield like that in this region. But in this 5 hydrogen also we can identify 3 different regions. So there is a symmetry along this axis. So the C, both of these hydrogens would have the same chemical shift, and these 2 hydrogens will also have the same chemical shift, and this hydrogen will have a different chemical shift. The signals for the Hc, Hd and He protons, they overlap. You see here, because the electronic effect of an ethyl substituent is similar to that of a hydrogen. So all of these are going to be in this area, close to 7.2. And then if you look at A and B, A is 3 hydrogens going to split to a triplet due to the 2 adjacent hydrogens. So this is a triplet. And then the B hydrogens, that is going to be your 2 hydrogens, will split into a quartet. You see, quartet due to the neighboring 3 hydrogens. And this is nitrobenzene. Earlier it was ethyl benzene, now it is a nitrobenzene. Nitro is a electron withdrawing group, and due to that it can create electron density difference between the A, B, C hydrogens on benzene ring. Okay. Now there are going to be 3 regions. These 2 are going to be the same environment. These 2 going to be the same environment, and this is going to be the same environment. And this hydrogen A. So this is A hydrogen is going to be this peak, and this B hydrogen going to be this one hydrogen, and then the 2 hydrogens which is going to be closer to the nitro group going to be further downfield right there. Okay, and this can split to a doublet due to the neighboring hydrogen. So you can see a doublet right there, and then this can again be a triplet due to these 2 hydrogens. It's a triplet. Okay, and then A, these 2 hydrogen can be another triplet due to these 2 hydrogens. The signals for HA, HB and HC protons do not overlap like the previous one because the nitro group is strongly electron withdrawing, and due to that they have different chemical shifts and we can separate them. Coupling constants. Coupling constants, J, given the symbol J, is the distance between 2 adjacent peaks. Between the 2 adjacent peaks of split NMR signal in Hertz. Coupling constant. So between A and B, the coupling constant. So it's measured between these 2 and measured between these 2. JAB. And also you can look at JBA. These are going to be JBA and these are going to be JAB. Coupled protons have the same coupling constants. JAB equals JBA. These are some coupling constant values. Types of protons. If you have on the same carbon, you have different hydrogens. HA is different than HB. On the same carbon, their coupling constant is approximately about 12. Okay. And then if you have a coupling constant, you have 2 hydrogens on alkene as a trans hydrogens, they experience higher coupling constants about 15. Okay, and if it is going to be a cis one, it's about 10 cis hydrogen coupling constant. And then the hydrogens next to adjacent carbons, HA, HB, their coupling constant is less than hydrogen on the same carbon if the HA and HB are different. But in 2 different carbons, HA, HB, so their coupling constant is about 7. But if it is 1, 2, 3, 4 bonds apart, we don't normally observe a splitting. Okay. Trans, it has a higher coupling constant compared to cis. And then if you have alkene and then alkene carbon carrying 2 hydrogens, different environment AB, their coupling constant is about 2. And then the long range coupling through a double bond, 4 bond coupling, 1, 2, 3, 4, they are about coupling constant 1. Summary. The number of signals in a proton NMR spectrum tells us the number of sets of equivalent protons in the compound. The value of the chemical shifts tells us the nature of the chemical environment, whether you have alkyl group, alkene group, and the benzene, or if it is closer to an electron withdrawing group, it's closer to a carbonyl group, oxygen, like that. Okay. And then the integration values tells us the relative number of protons. And the splitting tells us the number of neighboring protons. The coupling constants identify coupled protons. Coupling constants distinguish cis and trans isomers. Now this is a trans isomer. between A and B, coupling constant is about 14, A and B. You see, and that is due to the dihedral angle is about 180. When you have a higher dihedral angle, you can see it has a higher coupling constant. It feels more. But this is a cis 3-chlorophenoic acid. In a cis compound, dihedral angle is 0. So their coupling constant is about 9. Coupling constant for trans vinylic protons is greater than that for cis vinylic protons, and that is due to this dihedral angle. Splitting diagram for a doublet of a doublet. Now how do we make a doublet of doublet? Now let's look at HC, the C carbon right there. And this carbon, hydrogen on the carbon, hydrogen C, attached to another carbon where it has a hydrogen D, and then this carbon attached to another carbon, those are hydrogen B. So these B hydrogens and D hydrogens, they are not chemically equivalent because this carbon carries 2 chlorine and then this carbon carries 2 methyl groups. So the B and D hydrogens are not the same. And due to that, we cannot consider this one hydrogen going to split due to 2 hydrogens, a triplet. Instead, it would couple due to either D or B to a doublet. So remember, one will give you a doublet. And then each doublet will again become a doublet due to the other hydrogen, which is the B hydrogen. So that generates a doublet of a doublet. So this is HC. Chemical shift of the signal for the proton if there were no splitting. And then due to the B hydrogen, one hydrogen, this would split into a doublet due to the B proton. And then each one of these going to again split due to the D hydrogen, D proton, so that generates a doublet of a doublet. The splitting diagram depicts a splitting for the C proton of the compound into a doublet of doublets by B and D protons. And this is different from a quartet. So this is how the splitting diagram for a multiplet. Adjacent protons different or the same. When two different sets of protons split a signal, the n+1 rule is used separately for each set if the coupling constants for each set are different. The n+1 rule is used simultaneously for both sets if the coupling constants for each set are similar. Enantiotopic hydrogens. Now you can see this molecule, methyl group, carbon, and it has 2 hydrogens and OH group. We're gonna identify these 2 hydrogens as enantiotopic hydrogens because if you replace one of these hydrogens by a different atom other than methyl and alcohol, this generates an asymmetric center, meaning a chiral center. Okay, replacing an enantiotopic hydrogen with a deuterium or any other atom or group other than methyl or OH forms an asymmetric center. Now you remove one of these and instead of hydrogen you put chlorine here. Then you have an asymmetric center. So since that is a possibility that you can generate an asymmetric center by replacing one of the hydrogen with another atom, we call it as a enantiotopic hydrogens. And these enantiotopic hydrogens are chemically equivalent, meaning in a proton NMR they will give you the same signal. Okay, A and B are not different. Now there is another thing that is called diastereotopic hydrogens. Replacing each one of the diastereotopic hydrogens with a deuterium forms a pair of diastereomers. Now So this is our molecule. And the carbon, here I have a methyl group and then 2 hydrogens. And next to the carbon bearing these 2 hydrogen has an asymmetric center. Now we can replace, so these hydrogens can be replaced by another atom, let's say deuterium, and it generates 2 diastereomers. There is a possibility, right? So this is one and this is the other one. Excuse me. Since it can generate diastereomers by replacing with the deuterium, we call these hydrogens as diastereotopic hydrogens, and they are not chemically equivalent. So how do you find whether they are chemically equivalent or not? Look at the next carbon, neighboring carbon. If the neighboring carbon has an asymmetric center, then remember these 2 hydrogens are not going to be chemically equivalent, meaning this hydrogen can be splitted by this hydrogen B, and similarly hydrogen B can be splitted by hydrogen A. So HA would be a doublet, HB also would be a doublet. And then it can further split due to this hydrogen because 3 bond, 1, 2, 3. So this would be a doublet of doublet, like that. Protons bonded to oxygen or to nitrogen. Now this is a ethyl alcohol, CH3, CH2OH. So this is the CH3 group, and that is going to be a triplet due to the neighboring 2 hydrogens, and then the middle 2 hydrogens are here. That's going to be a quartet due to these 3 hydrogens, and this 1 hydrogen on oxygen can be a triplet due to these 2 hydrogens. Okay, and this is pioethanol, the first one, and then ethanol with the acid. You can see when ethanol is with acid, so this is a triplet, this is 3 hydrogens, methyl group is a triplet, and then the 2 hydrogen CH2 group is a quartet, and then the last hydrogen which is on oxygen is a singlet, ethanol with acid. Now let's see what's happening when ethanol is added with a bit of acid. In the presence of the acid, hydrogen on the alcohol can exchange. Now let's say this is a catalytic amount of acid. Alcohol, lone pair, grab a hydrogen and become a protonated alcohol. And it leaves a water molecule. And the water molecule is going to deprotonate the alcohol molecule. So it can deprotonate either this hydrogen or this one. If it deprotonate this purple hydrogen, you're going to get back this. But if it deprotonate the acidic hydrogen that was originally here, then you would end up getting hydrogen replaced with the original hydrogen with the acidic hydrogen, ROH. Okay, so in the presence of the acid you can see hydrogen exchange. It's not going to be in one place, and due to that the NMR signal will not be able to identify exactly what this hydrogen is doing. So because of that, that hydrogen will not be available for the neighboring hydrogen to split, and this will also come as a broader peak. The chemical shift depends on the extent of hydrogen bonding. Therefore, the oxygen-hydrogen signal is generally broad. Now, to identify if you have an alcohol group due to this exchange, what we can do is we can add a little bit of deuterium. And deuterium cannot give a proton NMR signal. Okay, and because of that, we will not see an alcohol peak. Deuterium signals are not seen in a proton NMR spectrum. So this can be identified in the proton NMR, and you add deuterium. So the proton exchange takes place. Instead of hydrogen, now you have a deuterium on alcohol. So this will not be seen in proton NMR. OH signal can be identified by taking the spectrum, adding D to O and taking the spectrum. And then the OH signal will be less intense in the second spectrum because now it is a deuterium instead of alcohol. So that concludes our chapter on proton NMR, and then we'll talk about the carbon-13 in the next